As I said in the previous video, the pH of buffers isn't always 7. They resist changes in pH, they neutralize invading acids and bases, but that doesn't mean they have to have a neutral pH themselves. The pH of the buffer is determined by what acid and base combination, weak acid with its conjugate base or weak base with its conjugate acid, you have, and also what their concentrations are. Whether we have a weak acid or weak base buffer, it becomes, or it is called, an ideal buffer if you have an equal amount of your acid with its conjugate. That doesn't mean that it's the best buffer for your situation. That doesn't mean that it's the strongest buffer or it's able to buffer the most, but it has the ideal ratio of acid to base. Sometimes we would want a different ratio for a variety of reasons, but that ideal buffer means that we're just as good at neutralizing acid because I have the same amount of conjugate base as I am at neutralizing base because I have an equal amount of conjugate acid. If we wanted a buffer with a slightly higher or lower pH, we would just need to tweak or adjust the amounts of weak acid and weak base that I put into it. So once again, the ideal buffer in terms of definition only is an equal amount of those two with a pH equal to the pKa, which then makes it just as good at buffering acid and base. If we wanted our pH to be slightly lower than the pKa, I could put in extra acid relative to the conjugate base. That would make it better at buffering base than it is at acid, but it would meet that new pH requirement. If I wanted the pH to be maybe a little bit higher than the pKa, I would need to just tweak that by putting in extra conjugate base. And this goes back and practices and helps us think about that relationship of pH to pKa in terms of the predominant species. When we're trying to understand, maybe predict, or apply this, there's a helpful equation called the Henderson-Hospital equation. That's really just a rearrangement of the Ka. So this equation didn't even used to be given in the AP equation sheet because it's just the same thing with a couple negative logs thrown in. But if we wanted to predict our pH a little bit more quickly, we could take the negative log of the Ka and then the log of the ratio of our base to acid. So that's given for us. And in all of these scenarios, we can do math to understand the exact pH, but we can also be able to do some predictions, connecting that no matter what buffer we're trying to make, ideal or not, when we are choosing the chemicals to make a buffer, we always want to think about the pH is going to be close to our pKa. So this has some predicting as well as some math with this equation.